what if Einstein's two biggest ideas, relativity and gravity, what if they aren't the final word? What if they're just the visible result of something, well, something deeper?
You know, what if things like time dilation and curved spacetime, what if they all emerge from some hidden microscopic structure? Well, that's exactly what the MMU framework proposes. Now, this isn't established physics, not yet. Think of it as a framework, one built on geometry and elasticity, where Einstein's physics is just what we happen to see on the large scale.
Okay, so how on earth could that even work, right? Well, the MMU's starting point is pretty wild. It replaces that smooth, continuous fabric of spacetime we all know with something totally different, something discrete, kind of granular. It's a hidden spacetime lattice. And the fundamental building block of this whole lattice is something called the cell. The best way to think about it is like this. It's the tiny elastic atom of spacetime itself, and it's got this very specific dual-tetrahedral shape. Now, the really cool thing about this cell is its hidden internal life. It's got these three internal coordinates. You can think of them as modes of vibration, and they're labeled W2, W3, and W4. But here's the catch, and this is crucial. We can't see them directly. They're not directly observable. We can only see what they're doing through their projection onto a single observable axis called W1. And get this, each of these hidden modes corresponds to a different kind of physical reality. So W2, that's the electric mode. Then you've got W3, which is related to torsion or twist, and in this model, that's what gives rise to spin. And finally, there's W4. This is the big one for our story, the volumetric mode. It governs compression and expansion, and as you'll see, it's the source of gravity. And here's what the complete structure looks like. The full cell is actually a dual tetrahedron. It's a combination of a tetrahedron and its inverse. And this duality is super important. It allows spacetime to be handed or chiral down at the micro level, but still appear isotropic, the same in all directions, on the large scales that we actually experience. Okay, so here's the crucial point. In the MMU, even time isn't a fundamental thing. It's not a primitive concept. Instead, it's treated as a projected observable, just a specific combination of those hidden internal dynamics. I mean, let that sink in. That's a radical departure from standard physics. All right, so we've got this wild new structure, but how does it build a unified picture of physics? Well, the central claim of the MMU is that all of physics can be derived from just one shared underlying dynamic. So instead of juggling separate laws for quantum mechanics, relativity, and gravity, the MMU says, nope, let's start over. It proposes they all begin from one single common origin, a hidden elastic motion happening inside these cells. And this equation you're seeing? This is the engine of the whole framework. Just think of each cell as a tiny coupled elastic oscillator. All its internal movements follow this one single master equation, where m is basically its inertia and k is its stiffness. And here's what connects everything: a universal scaling law. The stiffness of each internal mode is tied directly to the local cell size, which we're calling A. So what does that mean? It means if you squeeze a cell and make it smaller, it gets stiffer and it vibrates differently. This connection, this simple link between size and stiffness, that's the universal rule that governs the whole show. Okay, so we have all these new building blocks in place. The big question is, how do we get Einstein's physics back from all this? Well, let's start with relativity. In the MMU, it gets reinterpreted as a kind of geometric shadow. In standard relativity, time dilation is this profound, fundamental insight. It's a core idea. But in the MUM, remember, time itself isn't fundamental. It's just what you observe when those internal dynamics get projected onto that W1 axis. So time dilation isn't some separate rule you have to add in. Nope. It's just an observable effect of changing the geometry of that projection. So the visible rate of a clock changes, not because time itself is fundamentally warping or stretching, but because that hidden internal rhythm is being projected differently depending on the physical conditions, like when something is in motion. Suddenly, relativity becomes an effect of observation, just a change in the projected internal rhythm. All right, now for the other side of Einstein, gravity. And in the MMU, gravity isn't about the curvature of some smooth spacetime. It's much more physical. It's about the literal compression, the squeeze of the space-time lattice itself. Yeah, this is the key visual right here. Spacetime is this lattice of Earth cells. And gravity? Gravity is just what happens when this lattice gets physically squeezed or deformed. And what's driving that squeeze? It's that volumetric mode we talked about earlier, W4.
The cause and effect chain here is just beautifully direct. First, you have matter. The presence of matter activates that volumetric mode, W4. Second, this compresses the local Ur cells. Third, that compression causes the entire lattice to deform. And finally, when you zoom way out, this microscopic, elastic compression looks exactly like the smooth, curved spacetime of Einstein's general relativity.
And we can even write this down mathematically. Don't worry, it's pretty straightforward. The local size of a cell, A, is just its original size, A0, modified by this thing called a deformation field, U. And U is just a number. It tells us exactly how much that specific part of the lattice is being squeezed. And here it is. Here's the crucial payoff. When we look at this deformation U in a weak gravitational field, like the one we experience every day, it takes on a form that is incredibly familiar. It perfectly matches the equations of standard Newtonian and Einsteinian gravity. So the model works. It successfully reproduces known physics, but it does it from a completely different, much deeper foundation.
Okay, so we've got these two big reinterpretations. Relativity is all about projection, and gravity is all about compression. How do they work together? Well, this is where the framework gets really powerful.
This is where it all just clicks into place. Gravitational time dilation just appears. It emerges as a totally natural consequence. Think about it. Time is just a projection of the lattice's internal vibration, and gravity is the physical compression of that exact same lattice. So if you compress the lattice, you are automatically changing the geometry of the projection. And that makes a clock tick slower. It's like a 2-for-1 deal baked right into the geometry. So if there's one thing to take away about gravity in this model, it's this. Curved spacetime isn't the fundamental reality. It's just what microscopic elastic compression looks like when you're standing really far away. So to wrap it all up, the MMU framework offers us a path. It's a way to see the complex, established, and beautiful physics of Einstein emerge not from abstract rules and postulates, but from something simpler, something more mechanical, a foundation built purely on geometry and elasticity. And that leaves us with a really fascinating question to chew on. Could the elegant, profound physics of Albert Einstein, could it all truly be just the observable shadow of a deeper, hidden, and ultimately mechanical reality?